declarative visit imperative caching from Carl Davis. So take the floor.
Hi everybody, my name is Kyle, and today I'm going to talk about declarative versus imperative caching. So first off, I want to talk a little bit about myself because it's one of my favorite subjects. I'm the head of developer advocacy here at Redis Labs, and you can find me at these social profiles and as well as GitHub. Now, I live in Edmonton, Alberta, so I'm glad to be presenting at a Canadian conference. So let's first talk a little bit and do some level setting with regards to Redis itself. Now, Redis is an open source in-memory database. It's designed originally for very high performance things, but it's being used in a variety of ways, whether it's operational, analytical, or hybrid use cases. It's actually, and we just found out, we're the most loved database 4 years in a row, and one of the top 10 databases in use in the world, according to DB Engines, if I have my numbers correct. They change every month. So it's really widely used. Now, what Redis is a little bit more than just the kind of spiel that I gave you there. Redis nominally stands for Remote Dictionary Server, REDIS. Now, that's a little bit apocryphal. It was created by Salvatore Sanfilippo in 2009, so we just turned 10 last year. And I was actually interviewing Salvatore about this 10th anniversary and said, how did the name come up? And this was just a piece for camera. And he said to me, actually, the reason why it's called Redis is because I wanted a 5-letter domain name. And that became Redis.io. Redis.io is a documentation site for Redis. It also has links to download the materials and all sorts of things like that. So go ahead and check out Redis.io. It has everything to get started that you really need. But if it's not there, Redis has a kind of unique property to it. Redis is on BSD license, so it's completely open source. You can read the code on GitHub, and the GitHub is here on the screen. But what's really cool about it, it's written all in C, and it's written in really super clean C code. Now, I came from a generation of people that really didn't believe that it was possible to write clean C, and that it would just not create great software. But Redis has proven me wrong. In fact, the source code is really, really readable. And because it is readable, you can go and figure out what's going on. And if I don't find anything on Redis.io, if I'm trying to figure something out, I will actually just go over to the GitHub profile of Antirez, which is the creator of Redis/Redis, and look at the source code and find it out. It's so clean to read, and it's really easy and approachable. Now, if you look at the source code of a lot of other databases, that can't always be said. But Redis is a pretty concise, following some very common patterns, and so it's approachable to read and understand. Now, I work for Redis Labs. Redis Labs is the home of Redis, but it also provides Redis Enterprise. Redis Enterprise is basically the in-memory multi-model variant of Redis. Effectively, Redis Enterprise, what it does is it takes the core of Redis and uses it as kind of the atomic unit. When you're ever interacting with Redis Enterprise, you're effectively interacting with open source Redis as well, but it is very compatible with open source Redis, and it's 100% compatible as far as developing applications. But what it does do is provide you all of the operational characteristics. Now, Redis, when we say it's a multi-model database, it has pluggable modules that actually go into it and increase the data models that you can use. So, for example, you can change it into a graph database or into a search engine or into lots of different things, time series, and document database. And Redis Enterprise kind of smooths over all the operations of running those multiple different types of data models in a single database. It's really fascinating to see what it can do. Now, if you are a large organization, so you use a lot of Redis because you are a large organization, or you're a small organization because the nature of maybe the product that you're supporting, you use a lot of Redis, it has a real-time product or something, then Redis Enterprise is also for you. But you can certainly get started with Redis open source and even run small workloads on it. And then when you want to move it to massive scale, Redis Enterprise is there for you as well. Now, one of the things we're going to talk about today is one of the primary use cases of Redis, and that's caching. Now, to be honest with you, it is not the only use case of Redis. Redis, in fact, for Redis Enterprise that you see on screen, caching is only our #2 use case. In fact, the #1 is session stores. But caching is what people know Redis for, because it's quite good at it. But let's back up a little bit and talk about what caching is. Now, to go zooming out even further than that, we have to look at how most applications start. Most applications start in a very kind of naive architecture. They have one server, and I'm using a pizza box looking server that no one uses anymore. We usually just get an EC2 instance or something like that on GCP or Azure, some sort of cloud instance, and then they get a database. And you're launching your application on the server side, and you have your data stored in the database. This is pretty normal. Now, there is a differential here. Database products tend to be quite complicated, and there's a lot of things going on in a database. So at that point, your simple thing is pushing a lot of data into your database, and your database starts to really struggle to maintain load. And so at that point, what do? Right? You have your database, and it's not performing the way you want it to, or it's just struggling in general. The answer a lot of times is you use a cache, and the idea of a cache is quite simple. In this case, what it is basically this whole idea of writing still to your database, but reads are then encapsulated in a way that they can be written into the cache, and then out of the cache they are written or read from the application itself. So that really gives you a lot more room to move. So this is the whole concept behind caching. It's quite easy. Now, let's dive in and talk a little bit about why that works and where it doesn't. So performance is one of the ways that caching really does save the day. So in this case, we have pretty much the same setup we had before, but with a slight variant. You see the Redis symbol in the middle here. Basically what happens is, let's say you have a database query. It takes about 100 milliseconds to run that query. That is then loaded into Redis. This is called repopulation, or population, depending on which part of the cycle you're in. And then when the application requests the data, it requests it from Redis, right? And then that will take a much smaller amount of time, say maybe 1 millisecond. That's very realistic in Redis. Now, in this scenario, you can see that you have, let's say you're doing 100 different requests. In 100 requests, you have one request that's 100 milliseconds and 99 that are, 1 millisecond long. So the average time here is 199, or 199 milliseconds for the sum of all the requests. So the average time is, about 2 milliseconds, right? So in reality, though, most of them are actually kind of about 1 millisecond. So really what you have here is this kind of like reducing by a huge amount of time the overall request. Now, a couple other pieces on here. Now you notice there's the 60s, and I'm saying 60 seconds here. And in this, basically, I'm putting what's called a time to live or an expiry on the data. So that means that if I put some data into Redis and put an expiry of 60 seconds, data will be no older than 60 seconds. After about 60 seconds, Redis will say, I don't need this anymore, and we'll remove it. And then if we write our cache the right way, we will then repopulate again and start the process over again, and then repopulate from the database, pulling that fresh data in. Now, it can also save the day not only for just that performance way, but also from scale and load. And this is where we saw originally like that kind of red aura around the database. In this case, what you have is, let's say you're running 10,000 queries a second, and that's reaching the maximum of your particular database. Now, this doesn't necessarily reflect any type of numbers that you would normally have, but this is just an example. So what do you do in this case? You're getting a very high CPU load. You kind of run out of room in this particular instance of Redis, or of your database. So do you start clustering your database? Sometimes that's possible or easy to do. Oftentimes it's not. It can be expensive. You might have to buy licenses or whatever. Or maybe you don't have the ability to even do that if you've made some very serious mistakes in choosing your architecture. Let's just keep it that way. Now, if you put Redis here in the middle, basically this gives you a lot of options. So in this case, Redis is taking the majority of the read load off of the database and handling it itself, and so you greatly reduce the number of queries per second that you're actually doing on the database, and suddenly it's a lot happier. So this really helps out a lot. Now, you're thinking, this is great. Why don't I just do this for everything? Well, like a lot of things, it depends, right? But in the result of this is that you can't just cache everything. If you could, you'd just flip a switch on, and the database engine itself would probably have caching built into it. but things are not quite that simple. One thing to realize is that caching can be a detriment to your performance if you do it wrong. So in this case, you have a database query that's taking about a millisecond to run. You have a CPU utilization of 2%. This is not going to really help you a whole lot to put caching in, and in fact, it may hurt you. This is already pretty good, so if it's already good, don't bother, right? And that's really something you have to determine if you have the right kind of performance budget and saying, like, I want to get in this performance, what do I need to have to achieve that performance? Now, when you implement Redis, for example, in this scenario, what we're doing is actually looking at it in a slightly different way. So you have an already fast query, and you're populating it into Redis, and then you're taking that and you're taking it from Redis and reading it. So in fact, you think you might be getting something that's less than a millisecond, but in fact, it's actually longer. Why is that? Well, in this case, you're actually adding extra hops in that are not necessary, so you're increasing your overall latency. So that's not good. So think about that. Another problem you might run into is where the kind of thing that you're doing is not a really smart idea to cache. So let's take an example of like a user login, right? And this is vastly simplified, and I know that you probably have many more lines of code that will do everything you need to do to make sure that you're handling safely the data that's being submitted by a user when they log into your service. But let's just run with this for a second. We have some cache data at a particular key, and the keys are how Redis references data. We won't get into it too much here, but just know that a key is basically the way that you reference data in Redis. And we have the hashed version of the password that you have. So the user has this, it's already existing in the cache. The user says, hey, I want to change my password. That's fine. The hash password is written to the new database, or to the primary database. However, we have it refreshed it every 60 seconds if it needs to be. Maybe it's already in the cache, but you changed it in the database. So 15 seconds later, less than that 60-second threshold, the user logs out and then tries to log back in. They supply their new password, and they expect it to work. But they're checking versions of the cache, and the cache has the old password. And then it will say that password doesn't match. Now, I'm pretty sure I've seen this exact problem. Air Canada's site, I think, has this exact problem. I think it caches their passwords and doesn't refresh when you change the password. But this is the sort of thing that you have to really kind of think about it. So, you know, there's other things too. Like, let's say that you have a situation where you're caching everything, right? And when you cache everything, you have to understand that a cache is generally smaller than the primary database it's serving. It's a fraction of the size because it's using maybe in-memory databases or whatever. If you cache everything, you can fill it up full of useless information. So in this case, we're doing like sequential reads through like all these user IDs. That's probably not going to happen very often. So if you're indiscriminately caching, the important stuff that you want to cache is no longer there. So this fills your cache up with kind of useless information. So you kind of have to maintain that and think about what is the best use of that relatively expensive storage that you have. So we've introduced some problems. Let's take a look at what caching actually looks like in an application. I have some pseudocode here. We're doing a very simple SQL query. We're going to do take that query and we're going to hash it. When I say hash it, we're going to put that's going to turn that sequence of characters into a mathematical function and return a number. And that number will be represented probably by hexadecimal characters. Then we're going to use that to kind of create the key. Now, what we're going to do first is we're going to check for existence in Redis. If the key exists in Redis, or actually if not, if it doesn't exist in Redis, we're going to go ahead and just get the data from the database. We're going to store that in a local variable, and then we'll take the key that we generated from that using that hash in the query, and then we'll take that and put that as the key, and then we'll take the data and put that as the value, and we'll set it. So now we have a key value pair stored in Redis. We'll set an expiry on that key and say we don't want it after about 60 seconds. Then we'll go ahead and send the user that information out. So we're always sending from Redis. So we're always making sure that we're getting that code directly from Redis. So it's very consistent. Now, that's fine and good. And this is a pretty simple thing that you see all over the place. Let's say that you decide that you want to see if it doesn't need to be cached. You're kind of doing kind of a performance budget testing that we talked about. In this case, we just comment some lines out, and then we're moving some things around, and then we run it, and we want to keep it that way. I don't like this. I think this is kind of terrible, and I'll tell you why. There's a few reasons. One, it creates a ton of boilerplate. Two, you're commenting out stuff that's not code, which makes it hard to understand. You're introducing subtle bugs into the code. You're doing a lot of tight coupling, and then the real world of all this logic gets kind of complicated, which we'll explore a little bit later. So let's dive into these each by themselves. The boilerplate creates a lot of hard to understand code. I mean, we have, what is this, like 8 or 9 lines of code to do something quite simple. Six useless lines of code. The problem is when you comment something out in your code base, I know we've all seen this, it tends to be sticky. It doesn't get removed properly. So it just adds to the lines of code. So you look at your code base and you say, I have 20,000 lines of code. How much of that is commented out, right? And this will add to that problem. Then you take a look at the clarity to junior staff. If a junior staff member starts reading through this as they're a developer, they don't know why that's commented out. Does it not work? Is it something that we did in the past and we took it out for a reason? It adds a lot of extra questions. So it's really kind of not super clean, right? Now, let's kind of move on to this subtle area for bugs. I did a little trick here. I kind of flashed the screen white and changed some things on you. In this case, why do things look weird? You try to run this, it's going to say, no, it's not going to get you the right results back. It's going to say maybe like not found or maybe a SQL error or something like that. You catch the bug? Well, the bug here is that you're actually going to, you're getting the key and sending that into the SQL database. It's going to return an error, right? Instead of doing it from that, it should be query there, and you should comment out the line that says key. So it has some problems. Now, this is pretty easy to reason about what's wrong with it. Now, here's a more subtle bug that is kind of nefarious. This will be really bad. This is something you don't want to see in your code because it is the worst kind that works sometimes, it doesn't work other times. So let's say you're running this, right? It could give you some results sometimes and no results other times. Why? Well, in this case, what it's really doing is you're taking and you're getting it from Redis, but you're never actually populating the query. So let's say that you run this after a minute and you have an expiry on it. Well, that minute will go by, and then all of a sudden your data will be gone. Maybe it'll work for a little bit, and then it'll stop working. This is kind of the worst case scenario. So keep in mind that the subtle bugs are there. Now, let's talk about the coupling of data, right? When you're coupling data together in Redis, basically what it does is, or coupling the data and the cache and the query together, you're relying on repeatedly accessing the same thing over and over and over again throughout your code, because you're probably going to be doing this on a large application dozens and dozens of times. So if we take a look, here we have this, and we have a bunch of stuff that's referencing the Redis client. That seems fine, but you don't really have a very high-level abstraction when it comes to referencing that particular client. So you think, how often does a database library change? More often than you would think. So in this case, what we're really doing is trying to find a way to remove that. Now, why would you do that? Well, as an example, we just changed versions and we upgraded our protocol in Redis. So we expect a lot of different client libraries to change. And so maybe the way the code changed, the way that reflects in the code will also change because the protocol changed. And in that case, you're going to have a lot of lines of code to change, and it's going to be a pretty heavy job. If you had a sufficient level of abstraction, you would change it once, right? You're doing the same thing here with the database client as well. So if you change your database client, you also have this problem. You got all sorts of logic all through this. Now, the one that I don't have a slide for, but is important to note is I'm using a very simplified example of how you might do this in pseudocode. But when you start doing this in real life and you start having async await code or you start having callbacks, this gets much longer and much more complicated. So it is something to really keep in mind that you're going to do a lot of type coupling. You're going to have like a lot of lines of code devoted to this. There's got to be a better way. So let me introduce you to some just basic concepts, and I'll level set on them. We have two different types of programming here: imperative and declarative programming. Imperative programming tells you what and how to do something. Declarative, on the other hand, says what, but not necessarily how. So in this case, if you think about tying your shoes and you had to explain this to somebody, you'd have a very long description. You might take each lace in each hand and make loops and one over the other. That would be an imperative way of describing that. Now, declarative, on the other hand, is much simpler. It just says tie your shoes. It doesn't really care about how you do something as long as the end result is fine. Let's dive in a little bit further on that. Imperative is marked by things like if, then, and else statements, for loops, stuff like that. Most of the code we write, actually, is imperative. Declarative code is stuff like SQL, actually. Redis is imperative. HTML is imperative. I think this is the best example. If you are familiar with HTML, there's the button tag, and you have your angle bracket button, and you put what's in the button, submit or whatever the text might be, and you close it up. You're not telling the browser how to draw each line. You're not saying go up 25 pixels and go right 25 pixels and down, all that stuff. So that's, I think, a good way of thinking about this. Now, another way to think about this is thinking about two different things when what we're doing every day is feeding ourselves. And when we feed ourselves, we have two different options. We can get a recipe, and a recipe is an example of an imperative set of instructions, right? Take the chicken and put it into the batter, so on and so forth, right? Bring the oil up to 250 degrees and put the chicken in until it's golden brown. This is all just if-then statements, lots of individual steps. That's a recipe. Recipes are imperative. Now, a declarative is a drive-through window. You go to the drive-through window and you talk into the speaker and say you want some fried chicken, and then you pull around and then fried chicken is delivered to you. This is the difference. Now, how do we relate this to caching? When you have caching, we have this example here. You can see the if statements. We're doing a lot of different actions here. We're creating a ton of boilerplate. You're going to want to move things around. You're going to create subtle areas for bugs. Let's, on the other hand, take a look at how we might have this with a declarative model. And some background on how this would work, right? SQL is declarative, so having kind of something that matches that is important. In this case, we're going to make the caching the declarative as well. So what we're going to do is integrate the caching control inside the SQL query. Okay. The original idea of this was from a guy named Gaius. He wrote the Slonik client for Postgres for Node.js, which is how you connect Node.js to Postgres. And he had this idea of interceptors, right? It's kind of like a middleware for your query. So the query will be sent through a number of functions before it's actually sent to the database engine. Now, I wrote the Redis implementation for this, which integrates with Slonik and Redis. And you can find it at this particular GitHub thing. It's pretty simple. It's 50, 60 lines of code, nothing major. But let's take a look at how it will change imperative versus declarative caching. Imperative, this is the same snippet we've seen throughout this presentation. And we have a much simpler implementation on the other side. It's shorter, it has less variables, it is easy to read, there's very little to change. So effectively, implementing this sort of thing is just adding a few extra characters versus this is adding logic and areas for bugs and things like that. Let's take a closer look at actually what's happening here in the primary thing, which is the query, where we're actually going to be doing the caching and controlling it. So a closer look. Now I've been using JavaScript for over 20 years now. I hate to admit that, but in this, we have this tagged string. I had not seen this up until working with Slonik before, the Postgres client. Here we have that, and that's preceding the backtick string delimiters. So that's right there. And this just says, hey, we're processing this in a way that's not just a standard string processing in Node.js. Here, we're actually going through and controlling the cache. The dash is a way that you implement a comment in the SQL probing language. So in this case, if you don't have anything installed, if you're not doing this, this will be ignored. It'll show up in logs. It's perfectly valid, things for something like Postgres to receive. And then we have our standard kind of query in the middle here. So not a whole lot to really change. Let's take a look at what happens when we're looking at this from the perspective of Redis. So basically, Solonic will take this data and then print it through an interceptor. The interceptor will then start running some Redis commands. If we have to fill the cache, if this value does not exist in Redis as it stands, we're going to use the setex command, which is set with an expiry. We're going to generate a key. The key is going to be made up of a couple different things. We have a prefix, which we can define at the program level and the application level. And then we're going to concatenate that with a hash value of the entire query that we're sending. So this will make sure that when we're putting a prefix on the key value, or the key name here, we're doing that just so we're not having a big mess of unidentifiable keys in Redis. Oftentimes, many things coexist in one Redis instance. And then the hash is just there, so we'll have a nice, safe way, an easy way to reference it later on. The second argument here is 60. That's the number of seconds we're going to get this. If we had changed cache GTL to 120, that second argument on the setex command would be 120. And the value that we're setting there is the results from the table. So that's how we're filling the cache. Now, when we want to fetch from the cache, we're going to use the command get in Redis. And that is using the same exact first argument, which is the prefix. So we can basically deterministically get the cache, the key value for it. So one thing to keep in mind here is that this actually has a little bit of a weird quirk to it. If you put different cache TTL values in, you could have replication inside your cache. You can replicate many different keys over and over, or many different queries over and over again. This makes some sense. There's good reasons for this. If, for example, you had a situation where you had, let's say, many different cache values, you don't want them expiring early, right? You might want them to be the maximum. There's no good way to reason about this. So in this case, it won't store it multiple times, right? So if you had 60, 61, 62, 63, it would do a different one for each different query, right? So it's very literal. Those queries are different, therefore we will store them in the cache differently. So let's look at this as far as a demo is concerned. I will admit that this is pre-recorded. I found out that when I'm recording these talks, I can't actually reliably run a demo that gets anywhere near the CPU limits of my machine. So I did pre-record this, and you know, this is a true recording though. So I have a load generator that's running in one process on the machine. It's adding things to a Postgres table. This is a very kind of standard Postgres table. You have your user ID, your email, your username, and when it was created. So user ID is auto increment, so it's always going to go up. Created at, it's a timestamp, so that's just going to be whatever the Unix timestamp is. Now, I'll be running repeatedly insert into commands, and I'm using faker, which will actually generate fake data, so fake names and fake email addresses. Stuff like that. And I'm doing it every 50 milliseconds, so 20 times a second. So a pretty decent clip. Now, the other thing I'm running is actually the demo itself. That has kind of a hard query. I'm doing a relatively unusual thing. I'm counting the number of users get over in a table with a given pattern, a regular expression pattern. So in this case, I'm looking for Yahoo or .com or Gmail emails that are coming that I'm getting randomly, right? So then I'm saying to cache it for 10 seconds, right? This is actually something that is kind of hard to do. The more items you add into it with the insert into and the load generator, generally the longer it will take for the query to run. So it's a pretty good use where you would want to cache that data. I'm running this every 50 milliseconds, so 20 times a second, and it will run pretty easily. Let's take a look at this and how it works. So first things first, I'll play this. So here I'm starting this part, which is the actual caching demo. We've got the load generator on the bottom. Okay, so now we're getting our times back. There's some startup time here, so it's going to trend down a little bit and then start going back up. Here we go. So we're talking about running our query in 16 milliseconds or so, and we stopped it. And now at this point, we're going to go ahead and add in the caching. So I'm just going to paste in that caching TTL10, and then I'll restart the thing here where we're getting our cache values. And you can see it's already dropping. We're down to about 4 milliseconds. We're going to turn the population step back on, so we're adding more active data in. That will increase the response time because we are pulling more information from the CPU in general. But we see we're still settled down in about 4 milliseconds, 4.2 milliseconds, where we're up over 16 milliseconds. So we're around about 4 times faster. You can see if you look at the email count, we're at 2291 because we have a cached value. The I is how many times we've run it, and we can see that just went up to 2415. So basically, you can see where that went from 2291 up to 2415. That's basically where we pulled new values in. So simple. We are able to toggle in and out that value just with adding in the little SQL comment. So good time to talk about limits to this, what this can do and what it can't do. This is cache aside. Cache aside is basically one of the common caching patterns. Caching patterns basically say you have a read through, cache aside, write through, write behind. This describes how the cache is being related to the database and to the application itself. Cache aside is being run mainly through the application. So the application, Postgres and Redis don't really know anything, but the application is actually orchestrating the data between the two of those. Redis supports write through and write behind as well. It's a little bit more complicated to get running on those, but basically that allows Redis to actually make the writes directly to the SQL database instead of the other way around. So there's a lot of great use cases for that. Check out our blog, redislabs.com, to find out more about that. We are using Redis in a very minor way here. Basically, Redis has a number of rich data types. These things are like hash maps and lists and sorted sets and sets, all these kind of really fundamental data structures. We're not using anything of that. We're just storing blobs in Redis. In addition, Redis has modules that can allow you to store things as documents and all sorts of really, really rich things. Nope, this is just Redis as a blob. So when I say a blob, it's basically just a bunch of bytes that are being stored. So the entire table results are being stored as a series of serialized bytes. So there is an overhead for that. Now, it has some sensitivities. Similar queries, it won't do anything intelligent for that. So some query ideas will actually say, hey, do we already have something like this? Let's not query that or provide some sort of intelligence. It's somewhat dumb. As long as you put in those SQL comments, it's going to just cache it. And the TTL differences will cause the data to be replicated over and over again in the database if you don't kind of control that. So if you have 25 different TTLs, the same data may be stored 25 times in your cache. So that's something that you have to kind of just do by adjusting your source code and adjusting the queries that you're running. This is currently only in Postgres and only on Node.js. Redis is, of course, works anywhere. It's widely used. There's client libraries everywhere. But this particular, declarative caching right now is Postgres and Node.js only. I am currently writing the MySQL variant of it. It's a little bit more complicated because we don't have the hooks built into the client library. But I'm doing that on the stream on Twitch. Actually, if you're interested, may be already completed by the time you see this video. Then we'll maybe look into Python and some other different types of languages as well. If you use an ORM, for example, this is not going to help you a whole lot. So one more thing, since we have some time today, I do want to talk about Geo Local Caching and how that might help you. Geo Local Caching is an interesting problem. So here we have, I know we're in Canada. Canada doesn't fit on the screen as well as the US does. But let's say that we have a situation in the US as being a very wide country. We can have some very serious latencies from east to west. So the best case scenario, if you were to take and shine a laser from one coast to the other and somehow got over the arc of the earth, if you're a flat earther, I'm sorry, I can't even deal with it. But if you had that light beam to go across, it would be 40 milliseconds, and that's the fastest we can go, right? Is the speed of light, no matter if it's electrons or photons or whatever. So the realistic, if we're sending data from coast to coast, the best case realistic is about 85 milliseconds because it's not going in a straight line and it's switching latencies and all sorts of things like that. So 85 milliseconds is actually an incredibly long amount of time. At Redis Labs, we talk about things being instant and being under the threshold of human perception. So does it actually take less time than we can perceive? And that's the goal, which is 100 milliseconds. So already 85 milliseconds, that's just the data being transferred. That's the latency. So you're not going to get into that 100 millisecond less than human perception threshold. So let's say we have a user in Boston and we have our data center or our cloud instances on the West Coast. That's going to be bad. Even though we've implemented caching, it's not helping that situation. Now, another thing you can do is set up a West Coast or East Coast caching and then have your primary database in one location. Well, there's some problems with that too. Basically, when you do a repopulation step, you're going to have a very long latency to repopulate your cache, and that's not going to be good. 85 milliseconds. Not to do anything else, just to repopulate your cache. That's going to take forever, and it's going to really drive up your entire response times. So how do you solve this? Well, there's some good things that you can do. Redis Enterprise ships with this idea of active-active synchronization. This allows multiple different databases to be read from and written to. So in that case, what you can do is you can have one primary database and caches all over the place. I'm showing two, but you can have multiples. And when you do that, you can write either place and it will automatically replicate to the other place. And if you're using any of the rich data types, it will resolve conflicts as well. So you're getting more than just last write wins. You're actually getting kind of more atomic resolutions of these things. So in this case, basically, you can go ahead and repopulate your cache from either side, and it will automatically update the cache on the other side, yielding a situation where you don't have to manually do that or have differential caches. So in some situations, let's say that you're in Boston, but you get routed to the West Coast cache for whatever reason, some quirk in your connection. You'll always be seeing the as best as possible based on physics, the most up-to-date data, right? You won't have one that's lagging behind the other in any significant way. So that's about it for today. I do want to give you a little bit more. Go ahead and grab the module. It's available on GitHub, and then you can install it through npm. You actually don't have to go to GitHub to do it. Just npm install Slonik-Redis-cache if you have Node installed on your machine. You can play with the demo that is available on GitHub, and it's PG Redis declarative cache demo, as you can see right there. Follow me on Twitter, of course, at StockholmUX, and that's a long story why it's that. I'll have to tell you sometime when we can meet. Make sure and watch us, the whole team. There's three of us on the team here, and we all regularly stream on Twitch, so it's a great way to get inside the mind of a developer of Redis. And then shameless plug, do subscribe to my newsletter, Redis Watch. It's a monthly newsletter, talks about all the things that are happening in Redis, and we kind of make it fun. So it's it's something where you're not going to get spammed, right? It's just a subscription to the newsletter. bit.ly Redis-watch. All right, I hope you have questions.
Thank you, Kyle, for this interesting presentation on Redis. It was really, really informative. So let's open the floor for Q&A. We got one that came in from Sammy, and here it goes. In that microservices world, where each microservices can have many replicas, suppose we're using local cache in our application. Do you think Redis is a good solution to sync a local cache into different replicas? Or do you think it's better to store the data in MySQL database, for example, or get data from Redis?
Yeah, thanks. That's a really good question. In fact, it's really interesting you said that. I wrote a book recently called Redis Microservices that goes over this in detail. You can get a free copy on redislabs.com. But in short, yeah, you can absolutely do local cache syncing. If you have to use a couple different structures for that, I would suggest using the streams data structure for that. And have multiple different caches listening to different ones. But the canonical example would be to have one centralized cache that has many replicas. At the end of the presentation, when I was talking about active-active sync, that's kind of the best case scenario there. So you basically have your local caches running alongside whatever decentralized architecture that you have, and then they are being populated by another place, and you have other services listening to those changes and then can update automatically. So there's lots of different ways to do this, and it really kind of depends on your exact architecture, how it might be best for it. But certainly there are options there, and that's a pretty common thing we see. Microservices are a fantastic way to build applications. They can really take the complexity up a little bit, but at the same time, you get a lot of benefits out of it. The one thing that's about microservices are they're really intolerant to latency, and Redis can really help you have a lower latency in your data layer.
All right, guys, that's nice. Good answer. The answer is pretty clear. Would it be possible for you to actually post the link to the book on the Redis Lab in our chat for if
Sure.
people didn't have a chance to to pick that up, because it's probably a pretty interesting read. One other question that came up is how should we monitor our Redis deployment to assure that we can adopt a proactive mindset instead of a reactive one?
Sure. There's a lot of different ways of monitoring Redis. Internally, we actually we dog food our own system. Redis Enterprise includes Redis time series, and that's what we use to monitor a lot of that. But there's lots of plugins for various things out there. Redis time series, for example, integrates with Grafana and all the other kind of things you would normally see. But the most basic thing and the thing that's available anywhere is to just look at your slow log. Redis has built-in slow logging, and you can really start to see these things going up in it. Another simple thing to do is to look at, there's a free tool available on redislabs.com called Redis Insights, and that gives you out-of-the-box kind of very basic monitoring of any given Redis instance. You don't have to use our Redis instances, just open source or even other cloud vendors. And it will tell you all sorts of things. And in fact, it can do an audit of your data and tell you where you have large keys or what keys are incredibly busy, all those things. And it's a great GUI just for Redis to manipulate it. So Redis Insights, and I'll put both of those things in the chat window.
Thanks, that would be appreciated. Another question that we often see or hear is there any known implementation that we should try to avoid with Redis or that we're looking for trouble going that path?
Yeah, there's a few things. So Redis is actually, I've described it as checkers, right? Not chess. You know, checkers is pretty easy to learn the moves on, but getting the combos together can be kind of interesting. You know, learning it is not incredibly hard. There's a couple things to avoid though. The one thing to avoid is the command called keys, Keys, and that will give you all the keys that are available in your database, which is fine for debugging purposes. But Redis is a database in which it will do whatever it takes to get you the result. And people start out having a few dozen keys, and then they'll end up having several million at the end, and Redis will be busy giving you millions of keys instead of doing actual real work. So that's one thing that will really be critical to avoid. The other thing to look at is making sure that you have a proper distribution of keys when you move into clustering. When you're clustering Redis, every key goes directly to a single shard of the database. So one key is never on multiple shards. But as a consequence of that, if you end up creating keys that all go on a single shard, there's ways to kind of control where they go. You're going to end up creating something that will centralize the resources all onto one machine in the cluster, which will be very resource intensive. So when you're building out an application, assume that you will eventually move into clustering. And when you move into that, make sure that you are building it in a way that does not centralize that data onto one individual cluster. There are some controls that for people want to do things with, for example, transactions in Redis, which is a whole nother subject, where they'll try to put keys together and they end up creating a 10 node cluster, for example, that has one very busy node and 9 nodes that are twiddling their thumbs. So that's something to keep in mind as well.
Great, that's good. And in the world where the security is always one of our main concern right now, is that and with Redis, a lot of the data will be stored into our memories. Is data encrypted by default? And or if not, what is the best practice, or how should we secure our information?
Yeah, it's a great question. With regards to how you're doing security in Redis, there's a couple things to keep in mind. Redis is running on your server, and if you have a situation where you have somebody able to read the memory of your application, they have root access, and you have much bigger problems than mine. So many times encryption is a secondary thing. So keep that in mind. Of course, there's a couple of things around that. You want to make sure that you're encrypting on the way in transit, on the way in and out. So there's different options for that. Redis 6.0 actually includes a couple, which came out just a few weeks ago, includes a few enhancements for security. The first thing is it does have built-in TLS. The second thing is that Redis 6.0 introduced the concept of ACLs, access control list. So you can actually control where who can access the keys. In the past, Redis had no concept of users. You had a password to get into it, and then you had full access to the entire data space. Now with ACLs, you're able to say you're a user named Kyle, and Kyle can only access and run certain data and run certain commands. So that's a really big importance. But if you are in a situation where you are required by compliance reasons to encrypt your data, the thing to keep in mind is that there are options there. One of the things, and this is relatively new, there's a company called Anjuna, and Anjuna basically provides a security enclave. So this actually works with Intel SGX chips, and that means that you can create effectively a cordoned off part of the memory and processor that no other parts of the system have access to it, only what is kind of like required by communication protocols. So this will physically prevent anybody from reading the memory of another process. It's a very interesting technology. It is very early on right now, and it's not super widely available. But we did have at our conference, which was a couple weeks ago, redisconf.com, there's a presentation that's still available for free there, where you can see and they explain the entire security enclave part of the ecosystem.
All right, thanks a lot, Kyle, for this great answer.